Thank you. Thank you for the introduction, and I'd like to thank the organizers for inviting me and for making this seminar happen. Indeed, I will talk today about singular symplectic slice theorem, and this is a joint work in progress that we are doing together with my PhD advisor, Eva Miranda. So first, let me outline the content of the talk. So the main character here will be the slice theorem, but I will start with some motivating examples. First I'll talk about B-symplectic and BM-symplectic geometry to introduce where the singularities come from. And then I'll talk a little bit about superintegrable systems as promised. How do the non-commutative systems arise in this context? I'll talk about Slice theorem that's, well, first it will be symplectic. And then continue with two kinds of generalization of it. One in the case when singularities appears, and the other is when the action is not Hamiltonian itself. Okay, so let's pass to the introduction to BM symplectic geometry. Probably many of you know that B here stands for boundary, and sometimes B symplectic is referred to as log symplectic. So let's start with B without M for now. We call the B manifold a manifold with boundary, or a manifold an oriented manifold with an oriented exceptional hypersurface. Then you can also choose a defining function that vanishes along the hypersurface. Once you have that, you can also introduce B vector fields that can be seen as locally generated by these guys here, like especially pay attention to this one. And these are the vector fields that are everywhere tangent to the hypersurface. Once you have this, you can define the B-tangent bundle, which you can define by listing all its sections. And we say that the B-tangent bundle is the bundle, all sections of which are these B vector fields. And also, if you take a point outside the hypersurface, you may notice that it just coincides with the usual tangent bundle. And on the hypersurface is different. So as well, you can define the B cotangent bundle, and now you have everything to define what the B-symplectic form is. So in a sense, B-symplectic form is just a symplectic form, closed, non-degenerate 2 form, but in sense of B cohomologies. So in coordinates, like the Darboux theorem will be like this. So you have this dt over t term. Outside the hypersurface, again, if you check, it will be perfectly smooth symplectic form. But on the hypersurface, you allow this term. So once you have all of this, you can also define the BM symplectic form, where M stands for the order of singularity. So in sense of Darboux theorem, it will be like a sum of all negative degrees of t here. But you can go all the way down, starting with defining the BM vector field here. Yeah, you can do all of this business to define what BM symplectic form is. And formally, we again can say that BM form is called BM symplectic when it is closed and non-degenerate, again in the sense of BM cohomologies as a 2 form of this cotangent bundle to MZ. Okay, so if we look at it as a Poisson manifold, we'll understand that it admits an induced symplectic foliation. So the components, connected components of M without that will be open symplectic leaves of dimension 2n, and then that itself admits a corank 1 Poisson structure that's called cosymplectic. So the cosymplectic structure here is when we have an odd dimensional manifold Z, and we have a pair of 2 forms, a closed 1 form eta and a closed 2 form omega, such that wedge product of them with omega in n-1 power is a volume form on that. So for this structure, there is also a nice extension theorem that tells us that if we have our manifold Z as a submanifold of some bigger manifold M, and we have our pair eta omega here, that there is a unique way to extend it on the whole manifold, such that to a B symplectic form here, such that you'll have pi star of eta wedge dt over t having the B term plus pi star of omega, and this guy will be a B symplectic form. Okay, so the nice part about the theorem is that once you have it, once you found an extension, you know that it's unique. Then once we defined what is the structure on B and BM symplectic manifolds, we want to see what happens with the group actions there. There's also a nice theorem by Roshin Breder, Lana Kissenhofer, and Eva Miranda, proving that if you have a compact Lie group action that preserves your BM symplectic structure, that while on the covering space, it splits into the product of actions S1 times H that are respectively tangent and transverse to the foliation. So you have like action splits like this, where this is, well, this is our hypersurface. And that's an important thing, that the action that you have is not arbitrary. It always like has, well, it may not have S1 component, but it always, like, if it has, it always splits into a product like that. And then H is an arbitrary group that acts on the leaves. Yeah, and that's what happened on the covering, but sometimes on the manifold itself, it can be quotiented by the finite group that comes from the isotropy group. Okay, so once we have this, the only missing element for our business is the moment map. And let me first remind the definition of usual Hamiltonian spaces to see what we need for the singular case. So we call a Hamiltonian space a symplectic manifold together with a moment map that maps from the manifold to the Lie group, to the Lie algebra dual. Yeah, and then the moment map condition is that contraction of the form with fundamental vector field is exact. Okay, now we want to understand what will be the moment map for the singular action, and first let's look at the examples of actions that we're considering. So the simplest case here will be a nice symplectic Hamiltonian action when we have a sphere. We have an rotation by S1 here. We have our symplectic form dh wedge d theta. And the moment map is just projection on the H component, on the height. One way to generalize it is when the action is not Hamiltonian. So the simplest example here would be rotation of the torus, also by S1, when you still have symplectic form d theta wedge d phi. And your natural candidate for the moment map will be projection on the second circle. But then you understand that theta doesn't lie in the Lie algebra dual. So for this case, well, the reference, there will be a list of reference in the end of my presentation, but like first reference would be paper of Dusa Magdaf. I think it was in 88. And then the other case that we're interested in with our singularities is when we, well, in this case, we can just throw singularities on the manifold. You can do this always. Not any symplectic manifolds admits B symplectic structure, and not any B symplectic structure can be made symplectic if you take singularities away. But in this case, we can just put them there. So you'll have, again, a sphere with a singularity along the equator, rotated by S1, with the form dh over h wedge d theta. So you want to have some kind of moment map here, yeah, that I'll define on the next slide. And here, similar situation with the torus, you can throw singularities here like that. as an exercise, you can prove why you need at least 2 circles here, and you want to have a moment map, something similar to that. Okay, so let's define the moment map that we want to construct. Basically, in simple words, what we want is that our action should be called BM Hamiltonian if it preserves the BM symplectic structure, and if the contraction with the fundamental vector field is still exact. Yeah, so that's basically what's written here. But well, to understand where does it map, because like in this situation, for example, it mapped not to the Lie algebra dual but to S1 itself. Yeah. So here the map is to, again, Lie algebra dual, but tensor with these kind of functions that are constructed here in such a way that it's a direct sum of all the negative degrees of the defining function up to m, yeah, plus this b c infinity m, that, well, if here these powers could stand for d of some other negative powers, then the last one will be the d log. So you have this log term here, and that's a very important part of the moment map. So coming back to our example, we also need to understand what the moment map in B case would be. We can look back at our examples of sphere and torus. So to understand it in more detail, there is a paper by Gilliam, Miranda, Pires, and Scott. I think the paper is called B-toric actions, something like that. It's also in the list of references. But if you look at it, beware to look at version 1 on arXiv, because in the final version of the paper, this isn't present. But okay, so if we have our sphere with the singularity here, and we want to see our moment map, so we'll have the upper hemisphere, the lower hemisphere will project to the R, and then you'll have this minus infinity point here that comes from log module H. Okay, so the construction is that you can locally glue them with some exponents, and what you have is these 2 copies of R connected like this. And then for the torus, it's going to be pretty similar. Oh, sorry. What's happening? Okay. You again have 2 singularities. And your moment map, again, maps you to 2 copies of R, but now with 2 minus infinities here. Again, coming from our log component. And there is a theorem saying that for the surfaces, the image of the moment map will also be either B line or B circle. That comes from this kind of zigzag graph with these special weighted points on the edges. And, well, depending on the surface that you have, it will be either like this, or it will be a circle when you have, well, connected. And if you have high dimension, then it will be some kind of lattice. So that's, for now, that's all we need to know about B and BM symplectic manifolds group actions there. And let's, as I promised, let's talk a little bit about non-commutative integrable systems. So here is the definition that we have a Poisson manifold and an S-tuple of functions. So they form a non-commutative integrable system of rank R if they are independent, R of them are in the involution, and sum of R and S is dimension of the manifold, and then the Hamiltonian vector fields of the functions are linearly independent at some point of M. So you can see this F as a moment map, And if R is equal to S, you just arrive to the usual situation of a commutative integrable system. So we're interested in it because of Mishenko-Fomenko conjecture saying that they are in correspondence with the group actions on the manifolds. So some examples of them would be first a little bit generic example of non-commutative integrable system on manifold with boundary coming from some symplectic manifold and omega and upper hemisphere with the form bisymplectic form like that. So if you have a non-commutative integrable system of rank R on N, you can also consider this system on the interior of the product of your symplectic manifold with the upper hemisphere. And then once you double the manifold, you'll get the B-integrable system on the product of N with S2. So in the beginning, you have a perfectly symplectic form on the inside upper hemisphere, the same on the second half, and then you have exceptional hypersurface along the equator. So you can construct integrable systems like that. For example, like one of the examples of non-commutative integrable systems, symplectic ones would be Kepler problem. I don't think that I have much time to talk about examples here more, but I'll just mention that there are some examples coming from B-Hamiltonian torus sections, from geodesic flow, from Halilean group, and to see details on this, you can look at the paper called Non-Commutative Integrable Systems by Eva Miranda and Anna Kissenhofer. It's also in the list of references. So that's another examples that motivate us to think of Slice theorem. So let's now talk about Slice theorem. First, the most general case and why it is important. So if we have a compactly group and some abstract smooth manifold, first without any assumptions of the structure of it, we can look at the orbit of some point under the group action, and on the orbit map, we can define a quotient vector space like this that will be called slice. And basically, Slice theorem tells us that this diagram commutes. In other words, it defines us, lets us to look at the group action in the tubular neighborhood of the orbit. So the first Slice theorem that we are interested was stated by Palais, and it says that there exists an equivariant diffeomorphism from an equivariant open neighborhood of zero section to a neighborhood of the orbit on the manifold that sends zero section onto the orbit of X by the orbit map. Yeah. So that's the first version of Slice theorem, but the one that we are more interested in is symplectic or Hamiltonian Slice theorem, stated by Gilman and Sternberg. So most importantly, we are interested in it because it's the first step in modern Weinstein reduction. And this tells us that if we have a symplectic manifold together with Hamiltonian group action, then if we take a point such that its orbit is contained in zero level set of the moment map, then we take the stabilizer of the orbit, and there is a J-equivariant symplectomorphism from the neighborhood of zero section of the associated bundle that's equipped with symplectic model, and that's a symplectomorphism to the neighborhood of the orbit. Okay, so the other important theorem stated by Gilman and Sternberg is the local normal form theorem that gives us the linearization of group action and nice expression for the moment map. Yeah, so we are interested in this. Yeah, and that's used, well, okay, I won't explain much of it, probably just say that, okay, H0 here is annihilator, and it's kind of like this intersection is given the moment. Okay, no, I don't have time for it. Okay, So the theorem that we want to prove first, the first statement that we have, is the BM symplectic Slice theorem, but in this case for the BM Hamiltonian case. So we say that we have an S1 times H action, a compact group acting on our BM symplectic manifold, preserving the BM structure. Then we take again the orbit of the group contained in the critical set of M, and then there is a neighborhood of zero section of an associated bundle that will look like this here, equipped with this BM symplectic model, yeah, where pi here stands for the projection on the second component of this product, yeah, and omega comes from the symplectic form that's given by symplectic Slice theorem. So that's why I say that it's for the BM Hamiltonian case, because if you remember, well, maybe let me show it to you again. What we had here was kind of splitting of the moment map into two components, one coming from this S1 action that's giving us the log term, and the other just the usual moment map mapping into the Lie algebra dual that was Hamiltonian. Okay, so but nice part here, for example, is that this case without singularities, the blue one, was non-Hamiltonian, but once you consider it with singularities, this S1 action is allowed is just perfectly be Hamiltonian case. Okay, I hope this point is clear. So once we state this theorem, we also can say that the moment map in this case will have this form with, again, a log component. Oh,
Anastasia?
plus, yeah?
May I ask a question about the statement of the theorem? In that
Sure.
associated bundle, there's a subscript H, Z, cross Z. So is that an infinite cyclic group or a finite cyclic group?
No, I think, wait, it's a finite cyclic group. I think it's
okay.
it's missing there. I'm sorry. Yeah.
Okay.
Okay.
Thank you.
Yeah, thanks. Thanks for the question. I'm sorry for the typo.
So Anastasia, also don't worry about going a bit over time, because I mean we can be flexible, and there is time before the next talk. So
okay, but I think I'm okay. I'm
feel
gonna
free, don't rush. I mean, and take what you need.
Okay, thank you very much. So the moment map will be given by this formula with the log component, with other degrees of t, and this mu0 term coming from the Hamiltonian action and from the normal form theorem that we saw before. So let me maybe not give you the whole proof, but describe the model here. So first, what we do here, we say that the usual symplectic Slice theorem can tell us stuff about H action here. Yeah, maybe one important thing here, that here it's Hamiltonian, but we also want to look at the situations when it's not. And the last part of my talk will be about that. So symplectic Slice theorem tells us that there is, if you look separately at the H action, then there is an H equivariant neighborhood of the orbit of the point under H action that is symplectomorphic to this bundle with the symplectic form omega H that we saw before, yeah, on this bundle. So we can consider, if we consider our form here with P being the projection and omega H coming from the symplectic Slice theorem, then we can consider the quotient BM Poisson structure on the cotangent bundle to our group times the slice, where, so this finite group, thanks Raya, will act on T star S1 as cotangent lift by translations of on S1, and also it will act on T star H by cotangent lift. And on this I will comment later what the cotangent lift is in our case. And once you have this, you'll get the BM symplectic model associated with the vector bundle. So let's talk about cotangent lift in our case, which will slightly, well, okay, it doesn't differ very much from the usual one, but cotangent lift itself is a tool when you have any action raw on a Lie group of a Lie group G on a smooth manifold M without any assumptions on symplectic structure, not necessarily Hamiltonian or whatever, but once you have it, you can lift it to the Hamiltonian action on the cotangent bundle to the manifold. So here pi as a canonical projection from the cotangent bundle to M, and the idea is this diagram commutes, and our statement is that it still works for BM Hamiltonian actions. So you can lift an action on the B manifold to the BM Hamiltonian action on the cotangent bundle. So what we need here, we need to look at the Liouville forms. And if we have this S1 times the H action on the cotangent bundle, we can consider these coordinates that's split between S1 and H. And also, yeah, the Y is coming from R. So here H itself will be an n-1 dimensional manifold. And then it is equipped with a standard Liouville form. Then once we consider this form, we can see that the action of S1 times H on the cotangent bundle will be Hamiltonian with the moment map given by contraction of lambda, I think it's L here, with a fundamental vector field. So we can say that, well...
Can you go back to the previous slide a second?
Yeah.
So there is d theta divided by a to the power I?
Yes.
Ah, right. Okay. Okay, sorry.
Okay. So, like, to prove cotangent, the statement of the cotangent lift, we need to prove that the Liouville form is invariant under the action that we are considering. So L here will split into two parts, lambda H and lambda, yeah, coming from two actions. And we have to show that lambda H is invariant under S1 action, because for lambda itself, it already comes from the symplectic cotangent lift. Okay? Because of our product structure and the way how H acts on the symplectic lift. That's not hard to prove, to show explicitly by hand. And once it's done, the moment map can be written as this. And the form itself will have this form. Okay, so once this is done, the thing that we want to look to is desingularization. Because having BM form, there is a theorem by Guillemin, Miranda and Weizmann that says that if you have a BM symplectic structure on a compact manifold, then depending on whether M is even or odd, you can find a family of forms that will tend to our omega, that converge to omega, and in one case it will be a family of symplectic forms. In other case, it will be a family of folded symplectic forms. So folded symplectic forms are defined here. It's basically, again, the pair of two-dimensional manifold and two form such that the top power of omega vanishes transversally on Z that will be called folded hypersurface. Okay, why do we need desingularization? Why do we want to look at it? We want to look at it because of the reduction. So we know what is Marsden-Weinstein reduction for the symplectic manifolds, but we want to understand what happens with our BM symplectic case. One way to do it indeed will with going through slice, so that's this arrow, yeah, applying Slice theorem and then doing the reduction here. But another thing that we can do is to desingularize it and then to apply Slice theorem to this family of forms, yeah, to this convergent family of forms, and then to do reduction here. So reduction will kill the invariance of the action. It will kill the exceptional hypersurface. So here we won't have it anymore. And the question is whether this arrow exists, whether these two guys are the same. And well, if the process of desingularization is equivariant, then it should work. So yeah, that's our approach to reduction. And let me now go to the last part of the talk. I'll try to be fast here. The question is, what if our action, the H action itself, was not Hamiltonian? So in case of when the manifold, the structure is not singular, there are two approaches to that. One can be seen in the work of Ortega-Ratio. Another that I will be paying more attention here is both Tolman and Weizmann. So they prove Slice theorem for quasi-Hamiltonian spaces. And let me define quasi-Hamiltonian spaces here. So this is a generalization of Hamiltonian spaces with the moment map taking values in the Lie group instead of Lie algebra dual. It kind of has in itself the example of torus with circle and all that structure of Dusa-McDuff with S1 valued moment maps. So in this case, the statements of the definition has to be modified and the form itself is not closed anymore. It will also have some very understandable degenerations. But the nice part about it that it, well, the interesting part for us at least in this case is that, for example, any symplectic action that preserves symplectic structure but is not Hamiltonian will lead to a quasi-Hamiltonian space. So let me say a few words about examples here. Like one, as I mentioned, is that like for a Hamiltonian G space, you can construct a quasi-Hamiltonian space. Also for any symplectic you can do this. Then loop group spaces also are in one-to-one correspondence with quasi-Hamiltonian G spaces, which kind of kills the infinite dimensional part of loop group spaces. Then you can think of conjugacy classes as quasi-Hamiltonian version of coadjoint orbits. And another example that's of interest for us is the space of flat connections on the manifold with boundary. So if you take reduction with respect to the action of the subgroup of the gauge group that's identical at the boundary, you'll also arrive to a quasi-Hamiltonian space. Why do we need that? Because we want to prove the Slice theorem for this case and to kind of combine it with a singular case. So here, as I mentioned, to get a quasi-Hamiltonian space of Hamiltonian one, you need to do a very simple modification. You take a two form that's not closed and somewhat degenerate, a very particular form, that if you add it to omega, your omega will satisfy, if you add it to your symplectic form, the new form will satisfy its condition from the quasi-Hamiltonian definition, and the moment map will be just exponentiated, so you'll bring it from the Lie algebra dual to the group. And then what you get is a quasi-Hamiltonian space. We'll need this statement a little bit further, because what we want to do now is to look at the quasi-Hamiltonian local normal form theorem proved by both Tolman and Weizmann. That again gives us, well, for a quasi-Hamiltonian space, it gives us the, again, the diffeomorphism between zero section and the orbit, and also it gives us the expression for the moment map. So proving this theorem includes, well, two important statements. So one is that if you have, One is that if you have a quasi-Hamiltonian G space, you have connected neighborhood of 0 such that the exponential map is a diffeomorphism on U. Then you can take V, that's exponent of U, and there exists a Hamiltonian G space, and like the new one, that's equivalently diffeomorphic to the pre-image of the moment map of V. So the following diagram commutes. And to prove this, it's basically what we say now. If there exists this exponent, then we can take a logarithm and go back. And we also can take a form from which we extract this part. We already know what's the differential of this guy is, so that this will, the space that we're constructing here will be Hamiltonian, yeah, because we fix everything that was non-Hamiltonian before. And the other statement that we need to use here is the cross-section theorem. So if we have a quasi-Hamiltonian G space, and we have a slice for the action of G on itself, then we can take this guy. Okay, I believe there is minus missing here. The pre-image of the slice under the moment map. And then taking the centralizer of G, we can say that the cross-section, so this Yj that we just defined, the restriction of the form and the moment map, will be a quasi-Hamiltonian K-space. So I won't probably go into details with the proof here, but to prove the quasi-Hamiltonian local normal form theorem, what happens is that we first restrict to the cross-section, we look at it, and then we can apply that idea with taking the logarithm and go into the Hamiltonian space. So we'll get the moment map for the Hamiltonian case, and the last step will be to exponentiate it again. So yeah, this is basically it. And well, what we are working on now is on the combination of these two approaches when, if you remember, our S1 times H action is not Hamiltonian, so we know how S1 acts, and the action of H on the symplectic leaf is not Hamiltonian. So we are working on the case when the moment map sends the manifold to this Bm C infinity functions on M times G here. Okay, so the examples of these things can be constructed first basically as a product of two different spaces, but also they come from super integrable systems where you have non-commutative group action and singularities. Okay, so here are some references, and that's it. Thank you for your attention.